record on this computer. Okay. All right, now it's recording. So for those tuning in via YouTube, I think is where this will be on. This is the first week of hybrid sessions for Calc 2. So I know, so U-Sub is more of a review from Calc 1. Trig subs you're doing recently, integral by parts. You did like first 2 weeks. And then lastly, partial fraction decomposition, which is either what some are on currently or some will be in the next few days. Any questions about any of these?
Yeah, could you do a problem?
For which one?
Yeah, it was off the integration by parts homework.
Integration by parts? All right.
Yeah. It's the integral from 1 to 0 of y over e to the 5y dy.
Okay. Like that?
Yep.
All right. Okay, so this one for integration by parts, I'd highly recommend rewriting it so that it makes it a little more clear. So we can rewrite it as, so still 0 to 1, and then instead of y over e to the 5y, we're going to do e to the negative 5y. And there we see a simple u dv, and we can use that. So for integration by parts, you typically learn, so I don't know if everybody uses this here. There's liate or liat. People say liat, and I just like to add the a because that way you know that it ends with an e. But I use lipit, which is very similar in this case, and I can show you the differences. So L and I stay the same for both of these, and that's logs or logarithms. And then I is inverse trig. So that's your, not cosecant, but arcsecant, arccosine, arcsine, all that. So those stay the same. Now this A stands for algebraic. So that's your y in this case. It would also be like y squared, anything that's polynomial. And then P on this side is polynomial, so it kind of, it means the exact same thing, they just use different letters. And now you'll notice that the T and E are flipped here, and that's because this is trig and exponents, or exponentials. And so e to the negative 5y is an exponential. So the higher up on this list, the more you want them to be a u. So we know that the integral of u dv is equal to u times v minus the integral of v du. So through each iteration of these integrals, we're taking the derivative of u. And so these higher terms, like log and inverse trig, you can't take the integral as easily, which you would do if they were dv. So you like keeping them as the u because then you just take the derivative of log instead of the antiderivative of log. And for the reason why these two can be flipped, it's because exponentials and trig functions tend to work very alike when it comes to taking derivatives, as in they stay the same or they loop constantly. So you can kind of interchange the two and you'll get the same answer. So whichever one of these is easier to remember. I learned lipit. I know a lot of people here learn liate, so it's kind of preference. Nobody will mark you down for using one over the other. Yeah, so for this case, we have to figure out what we're using for our u and dv. Sometimes it's in this, or in this order, sometimes it's not. So we have an algebraic or a polynomial and an exponential. So exponential is at the bottom of the list. So we know that that's probably going to be our dv. So our u is going to be algebraic or polynomial, which is y. So I like to fill out a small chart. So u is equal to y, dv is equal to e to the negative 5y dy. And now we go down the list. So for the next one, we need v and du. So we find du, which is just the derivative of this, which is dy. And then for v, we take the integral of this. So if we take the integral, since we have e to the negative 5y, we have to do U-substitution slightly. When it's just a constant up top, I don't bother with it too much though. So since we know that taking the derivative of this would bring negative 5 down here, we have to instead divide by negative 5 because we're taking the antiderivative. So we get negative 1 over 5 e to the negative 5y. And don't worry about any plus c's right now because you can save that for the end of the integral. Of course, this is a definite integral, so we won't have that anyway. So now that we have our u, du, and v, we can fill out this portion. So we get y, so I'm gonna put that. So that's our u times v. And then we have minus, and then it's v, so we can put the negative 1/5 out front. We get plus 1/5 the integral, and it's so v du. So our du is just dy, so we're just left with this. And then, yeah, dy. And we can fill out the 0 to 1 afterwards. So again, we just took this integral, so we can just do it again really quickly. Just remember to multiply the 1/5 through. So we get negative 1 over 5 y e negative 5y. And then minus 1 over 25, then e to negative 5y again. And then we'd have a plus c, but we're just doing a definite integral. Was it 0 to 1 this way, or was it 1 to 0?
It's the way you got it.
Okay, just confirming. All right, so we evaluate at 1 first. So this is going to just be negative 1/5, and then e to negative 5. And then this one will be negative 1 over 25, e to the negative 5. And then we subtract the evaluation at 0, which will happen to be, so since both of these are negative terms, and well, so when y is equal to 0, this term drops out. Y is equal to 0, this just becomes 1, and we get, so minus 1/25, so plus 1 over 25. So you could write your answers this, or you could simplify. WebAssign is pretty good at simplifying it for you once you put it in. I've had times where I've had like an entry that's like the entire page width long, and it still accepted it. So don't worry about that yet. That's for Calc 3. So yeah, any other questions? We can go over different topics.
Number 12 on our homework.
Is that a exponential and trig one?
Trig one?
It would have exponential and trig in it, like e to the x and cosine x, because that would be the example I would do.
Oh, it's theta to the third times cosine of theta squared.
Okay. Say that again, and I'll write that down.
It's the integral of the square root of pi over 2 to pi. All of the limits I was saying.
What?
That was a limit.
Oh.
Yeah.
Yeah. Okay. So is that the bottom or the
Yeah,
top?
lower limit, and then the upper limit is the square root of pi. And then the integral is theta cubed times cosine of theta squared.
Okay. All right, so this one's slightly fun. So this is a kind of a combination of U sub and integration by parts. So since we have theta squared in here, we're going to need to kind of simplify it a little bit so we can actually, we're going to use U sub. We might want to use a different term though. So we're gonna call it W sub right now. So we're going to say W is equal to theta squared. U sub is just because U is a very easy term to use. But when you start using it too much, you got to change it up. So then dW is going to be 2 theta and then d theta. So what we can do with this then is we get, all right. So this will be replaced by W. Theta squared in here is going to be replaced with W, and then we have a theta left over that we can replace. So I'm gonna stop writing the bounds for a little bit, and we get, so W, and then because it's 2 theta, we have to divide by 1/2. And then we have cosine W. So we've already simplified it down quite a bit, but we still have to do integration by parts. So again, we go back to our rules here. So we don't have log, inverse trig. We do have algebraic and we do have trig. So what we can do from there is we say, okay, so trig is at the bottom. So that's again going to be dv. So u is going to be w. dv is going to be cosine w. And dw. So now from there, we take du, which is just dw. And then we take v. So integral of cosine is just sine w. And now we fill out this equation again. So we get this integral, and remember to keep the 1/2. So we're going to say 1/2 integral w cosine w dw is equal to 1/2 times, and then this is just going to be big parentheses. So we have uv, w sine w, times, and or no, not times, minus integral v du. So du is just dw, so the integral of this. So from here, integral of sine would be negative cosine. Because we already have a negative out here, we get positive. So we get 1/2 w sine w plus 1/2 cosine w. And now we can either choose to change our bounds to what it would be for w, or we can change w back in for theta squared, and then use these original bounds. I like to switch the bounds. So since we know that theta is going to be between the square root pi over 2 and the square root of pi, when we plug in theta squared for w, we get w is going to be in between pi and pi over 2. So we have pi over 2 on the bottom, pi on top. When we plug in pi, sine of pi is going to be 0. So we get 0 plus, and then cosine of pi is -1. So we get plus -1/2. And now we subtract the value of pi over 2, which, so pi over 2 of cosine is 0, so we don't have to worry about that one. We have pi over 2 times 1/2, So we have pi over 4. And then sine of pi over 2 is 1. So we're just left with that. And then, of course, that's 0. So we end up with minus pi over 4 minus 1/2. So negative pi over 4 minus 1/2. Oh, where did the, oh, I just realized the 1 over 25. The 1 over 25 came from, so back here, we took the integral of this. So when we take the integral of e to the negative 5y, that 5, we divide by the negative, or negative 5. So 5 times negative 5 is negative 25. That's why we have it on the bottom there. Hopefully that clears things up. Sorry, I missed it for so long.
I think I found one of the exponential in trig if you wanted to do one of those.
Yeah, that's probably what I was going to do next. We got a good example for it. Yeah, that one works. Okay. So I'm gonna use a new sheet for this because this one's gonna take a little bit. I have beautiful green paper now. That's semester old. All right. So yeah, number 18. All right, so here's another example of integration by parts that you will likely run into and is really helpful to get down because you'll see it often. And that's when you have an exponential and a trig together. And this will also kind of highlight why we can use both in either order.
Is that e to the negative theta?
Yeah, e to the negative theta. I can write that a little clearer. All right. So for this, again, if we go back to here, we have different orders for exponential and trig. You can kind of just choose whichever one you want. I would suggest, so let's see. Kind of depends. So since you have a coefficient of 2 in your trig bit, you have to determine whether you want to keep dividing by 2 or keep multiplying by 2. If you want to keep multiplying by 2, you make your trig your u, because then you take the derivative and chain rule continually multiplies it. If you want to divide by 2, you're going to make it your dv. So I prefer seeing the fractions here. I don't know, it's kind of weird. That's just how I like it. So I'm going to say that u is equal to e to the negative theta. And then dv is going to be equal to cosine 2 theta. So now we have to find du, we have to find v. So again, du is just the derivative of this, which luckily this is pretty easy because it's a -1 for the coefficient. So it's negative e to the negative theta. And then taking the integral of this, since it's the integral of cosine, it's going to be positive sine. And because we have a 2 as a coefficient inside, we divide by 2. Oops. 2 theta. So now that we have that, we now write out what this is equal to. And for this, it might actually help to continually write out the left side for reasons I'll get into very shortly. So again, 2 theta, it's going to be equal to, and then it's u times v. So 1/2 e to the negative, oops, I don't know why I did that. E to the negative theta, and then times sine 2 theta. Keep making small mistakes. All right. So now we do minus integral of v du. So we have du is actually something other than 1 this time. So v is going to be, again, we can put the 1/2 out here. and it's sine of 2 theta in there. And then so we get, oh, and since we have a negative e to the negative theta, we can put the negative on the outside, make it positive. So you get e to the negative theta sine of 2 theta. Now we can't easily take the integral of this either, so we actually have to do the same thing over again. So with that, we again state, okay, u is going to be equal to e to the negative theta. And then v is going to be equal to, or dv is going to be equal sine of 2 theta. And then du is equal to negative e to the negative theta. And v is equal to, so integral of sine is negative cosine, and you divide by 2 again. Now I have to write out this whole thing. Don't forget the 1/2, and also don't forget if you have a negative sign out here. That'll often mess you up and you'll get the wrong answer. Negatives catch the best of us. So we get, again, write out this, and you'll see why soon. And this is the beautiful thing about these, because they keep repeating. So we get 1/2 e to the negative theta sine of 2 theta. This is just the same thing that we had earlier. And then we get plus, and then it's 1/2 times, so it's u and v again. So you'll notice we already have a 1/2 there, so we can actually make this 1/4. 1/4 e to the negative theta cosine 2 theta. And then minus 1/2 and then times v again, so 1/4 the integral. Then it's v du again, so we have a negative in the du, so we can just make that positive. And we now get e to the negative theta and then cosine 2 theta d theta. And now, if you have sharp eyes, you probably notice that this integral right here is the same as this integral right here. So what we can do, and this is the reason why I kept writing this out, is since these are the same, we can kind of treat them as a group variable and say, so we have 1/4 of it on this side and 1 of it on this side. We subtract 1/4 of that, and we get 3/4 the integral e to the negative theta cosine is equal to, and then this whole thing. So 1/2 e to the negative theta sine 2 theta plus 1/4 e to the negative theta cosine 2 theta. And of course there's a plus c, but I'm waiting to write it till the end. So now, because we're solving for this integral, we just multiply everything by 4/3. And so we get, so 4, so we get 2/3 here. E to the negative theta sine of 2 theta plus 4 cancels, so we get 1/3 e to the negative theta cosine 2 theta. And then finally plus c, because this is an indefinite integral. Now, if I were to do this the other way, where this was our dv and this was our u, we would end up with the same thing. It would just work out a little different on the intermediate steps. Instead of fractions, we'd have like whole number constants. But it would end up the same because you'd end up having like 5 minus 4 of one thing or something. Yeah. Any other questions on partial fraction decomp, or not partial fraction, integration by parts? that kind of covers one of the hardest problems in the set. So typically you'll deal with more constants though, or weirder constants like 7. Let me show the top of the paper real quick. Yep. There. Leave it like that for a bit. I believe so. They'll tend to make it a lot easier. Like they'll probably keep it to like a constant, like 2 and 1. They won't make you deal with like, typically none of the homework problems either will make you deal with anything that's 2-digit. So you will sometimes have like a 2 and a 3 though. So be prepared for that. Yeah, really most of these just turn down to 2 iterations because it cycles back, and that's because of sine and cosine. Another reason why exponential and trig tend to be where you use dv instead. So, yeah.
So it would work just fine if you use u as a
Yep.
trig, right?
Yep. And that's why both of these methods work. So well, I guess I should say, yeah, both of these shortcut, or I guess guides is what they would be. So yeah, if there are no more questions on integration by parts, I can go on to another subject.
I got one more.
You do? Okay.
So it's the integral of 7 times the natural log of the cubic root of x.
Cubic root of x. Okay. All right. So here we have some unique tricks that we can do. So I don't know how many of you remember your log rules, and this is not log rules like integrals or derivatives. This is going back to pre-calc. So when you have a exponent inside of a logarithm, you can actually take it out and multiply the outside by it. And like I can kind of show you the proof of that. So if you have log base 2 of, let's do 8, all right? So log base 2 of 8 is going to be equal to 3, because that's 2 to what power equals 8. So 8 can be rewritten as log, so 2 to the 3rd power. And so we know log base 2 of 2 is 1. And so we can say that this is going to equal 3 times log base 2 of 2. And again, these are literally the exact same statements. This is going to equal 3. So yeah. So for this, we have the 1/3 power inside. So what we can do is quickly say, okay, we're not going to write this mess. We're going to write 7 divided by 3 natural log of x. And now you have to do a little fun bit, which is integration by parts. So although this doesn't have a variable in it, we can say that this is algebraic or polynomial. So we can say our u, of course, is natural log of x, and our dv is 7/3 dx. And sometimes you'll just see the integral of natural log of x, which you'll probably see on an exam at some point. And in that case, you just say that it's multiplied by 1 and your dv will be 1. So just giving you the heads up because you will probably see that. So for here, we then just solve du, which is just dx over x. And then we solve for v, which is 7/3 x. From there, we just do our little solve, which is, so u times v, so we get 7/3 x, natural log x, and then minus the integral, and then it's 7/3 x times dx over x, which simplifies to 7/3 dx, because we get x over x cancels to 1. And then we just get the simple equation. So this whole integral is equal to 7/3 x natural log x minus 7/3 x. So if we were to just take the integral natural log of x, this you can also memorize too, but you might have to show your work if you get this on an exam. We can simplify this to just x ln of x minus x. And that's a good pattern to remember. If you can at least remember it, you'll know if you made a mistake on the exam. And it's a pretty simple formula to remember. Not the most simple, but definitely easier than some integrals. So yeah. Was the 7 cube root of x? It was cube root of x. So this right here is cube root of x.
So if you want to just do that shortcut, you just pull 7/3 off front.
Yep. Yeah. I just figured it was more helpful showing first time how to do it, yeah. All right, we still got about 20 minutes left, so.
Yeah. The integral arctan of 2t.
Arctan of 2t, okay. That's gonna be kind of similar to this one, so let me, all right. So we're doing the integral of arctan 2t. All right. So this is very similar to natural log. Again, you're going to treat like there's a 1 here. That's going to be our algebraic polynomial. So we get u again. So arctan falls under inverse trig. So it's again same tier as logarithm. So you make that our u. So we get arctan 2t. And then we have our dv is just going to be 1 times dt. So then our du, if I remember correctly, it's going to be, so 2 dt over 1 plus 4t squared. I believe that's correct.
You want to do U-substitution there, or does that not matter?
I don't think it matters in this case. I mean, this is derivative, so it would be chain rule. I just kind of did that up there.
Yeah.
So yeah, don't forget chain rule for these, of course. Because yeah, I believe it's, yeah, because it's a du over 1 plus u squared. So our du is 2, and our u would be 2t, so u squared would be 4t squared. And then v is going to equal just t. So now again, we fill out our uv, so we get t arctan of 2t, and then minus the integral. This is where it gets messy. So now we get, so we have du and v. So v on top, so 2t, because we have the 2 there, over 1 plus 4t squared. All right. So here, I'm trying to think of what's the best method. Thinking, I forgot to turn my off too, I didn't realize that. All right, I think just U sub, right? Yeah. Yeah, all right, so we're gonna do U sub for this. Typically, you won't have to do the 2 iterations like we did with e to the negative theta cosine of 2 theta.
do you like determine when you need to use like substitution or not? Or like where you would use like integration like parts and stuff?
Yeah, I have the wonderful advantage that is multiple years working at the MLC, but what I find is if you can figure out, is there an internal function? So in this case, we have like, if we were to treat this as 1 over x,
Yeah.
we have a 4t squared on the bottom. So that's kind of like an internal function in there.
Okay.
And then we would use that as our u and then solve for du. And that's what I'm kind of doing in this case.
Yeah.
Luckily, there are only so many tricks, so.
I also look for things that cancel out. So I
Yeah.
saw there was a 2 squared up there.
Yeah.
your
And so
2t,
when you take the derivative of that, that's gonna be 2t.
Yeah.
Or well, like 8t in this case. And
Yeah.
so those t's will cancel out. So that's kind of the things I look for. So if I see something that will cancel when you take the derivative, that's something I look for.
Yeah. So in this case, yeah, we're going to treat, and I like to include constants like this because when you take the derivative of the entire u, this 1 would drop out. So we end up with something like this. U is equal to 1 plus 4t squared. Du would then be equal to, so this is 0, that would be 8t dt. So then, of course, we only have a 2t dt. So if we divide both sides by 4, we get 2t dt is equal to du over 4. So you can replace this entire thing with du over 4. So we get negative 1/4 integral of du over u. Oh wait, I already wrote the du, yeah. Because that's just substituted, that's already substituted. So this is just natural log of u, and then we substitute that in, or that. So negative 1/4. So now we just fill out the rest of this. So we get our integral is equal to t arctan of 2t, and then minus 1/4 natural log. And sometimes I think WebAssign prefers if you use absolute values. In this case, you don't really need to though, and that's because this is always going to be positive due to the t squared. Just keep in mind that if you ever get a problem wrong on WebAssign that has a natural log, don't immediately assume that you did everything wrong. Think if it just needs the absolute values. So yeah. And try the integral of sine cubed 5x. Yeah, I'm gonna need to remember how to do that.
I think you do u is equal to sine, right?
Yeah.
Sine squared is equal to 1 plus or 1 minus cosine squared. And then you do 1 minus cosine squared, u is equal to cosine.
Yeah, here, I guess let's write that out. Any questions on this one first though? No? All right. So let's do that real quick. All right, so we're going to do, so sine cubed 5x. All right. These are the ones that I always slightly struggle with, because yeah, typically you're going to try to figure out what you're taking out of here. So we have a, oh, I think what you could do. So since we have a sine square in here, we could say, so this is equal to integral of sine 5x times sine squared of 5x. This is typically the trick to doing trig subs. You separate out your powers. Typically you'll be left with 1 of something. And then sine squared, I believe, so if we use the sine squared plus cosine squared equals 1, we can say sine squared is equal to 1 minus cosine squared. And then we'd have So we get the integral of sine 5x and then times 1 minus cosine squared of 5x. And now what we can do is we can say that this entire thing is our u. So u is equal to 1 minus cosine squared of 5x. Du, so this would drop out. And we'd get, so derivative of cosine is going to be negative sine. The way to remember if it's negative or positive for derivatives specifically is if it starts with a c, because everything that starts with a c becomes negative when you take the derivative. So we get positive, so you have the 2 drop out, and then due to chain rule, you multiply by 5 as well. So you get a total 10 sine of 5x. And with that, let's see. Yeah, dx. So then we just replace this. So we have sine of 5x dx. So we have 10 coefficients, so you just divide both sides by 10. And we get, so, all right, 1/10 the integral of, and then it's going to be, yeah, just u du. All right, I'm doing this right? Seems too simple.
Don't you like cosine 5x du? So that's 1 minus u squared. So then once you plug it in for du, it cancels out the sine 5x. You're left with 1 minus u squared. Then you integrate that to u minus u to the third over 3.
You know, I think you're right. Yeah,
At least that's how I did it.
yeah. Oh yeah, the way I did it is actually wrong because the derivative here would have to go through a little more than that. I didn't do the chain rule properly, yeah. So you'd actually want, yeah, your u. Thanks for catching that. All right. Yeah, this is cosine 5x. And then this would just be 5. So then we divide by 5. And now we change this up a little bit. And we get 1 minus u squared. Yep. And that becomes a pretty easy integral in itself. So we get equal to 1/5, then integral of just 1 is u. And then integral of u squared is, so we have, so 3 is the new power, divide by 3, times 1/5, 1/15, because 5 times 3 is 15, u cubed plus c. And then of course we have to substitute our u back in. And we get 1/5 cosine 5x minus 1/15 cosine cubed of 5x plus c. So yeah, typically in these cases, you're going to be dealing with sine and cosine in various powers. Sometimes you'll have to deal with secant. I think secant cubed is the notorious integral, right, Sydney?
Yeah.
Secant cubed, yeah. Watch out for that one. They'll give you an identity eventually, I think. Oh yeah, good point. Yeah.
You take the derivative of u, isn't it? Is it negative 5 sine 5x?
Yes.
Negative 1/5.
Yep. And I think, do I need to deal with that negative in there? No. Oh, do I need to rewrite this again?
I just throw negative.
Yeah. It's like that. There. Negatives gets the best of us.
Yeah.
Yeah. You substitute 5x before doing the identity. Yeah, it'd be a 2-layered U-sub. So you could do it if you want. You just want to change what you're using for your U-sub. So like I use W as my backup. Yeah, you would just, so you would first, I guess in here, wait, where would you do it? Yeah, you do it right up here, change the 5x to like a W or a U, whatever you want to do. And then you go throughout all these steps still, and then so your U instead would be cosine of W, and then that would just be simplified because you'd just have a dW here instead. You'd still have a 5 as a factor, yeah. All right. So I guess we're getting ready to change shifts soon. I gotta figure out how I'm gonna I just send the recording to Paul and the repeater. Why did I call him Paul?
Patrick,
Yeah, Patrick. Patrick, Peter, Paul. How did I get that wrong?
did you record it to the cloud?
I recorded it to the computer.
Okay, if you record it to the cloud, then it just goes straight to his account.
Ah. Next time I'll
I'm gonna record mine, so you don't have to send it to me.
Yeah, okay. So let me, all right, so I'm gonna stop recording. In a couple of minutes, a new session will be up if you want to stay. Yeah. All right. So.
Just log yourself out.